Hi everyone. So welcome to the next video. This video is on process queues. Okay. So the moment I am saying process queue, it does not mean operating system maintains a queue of processes. So when I am saying a process queue, it means operating system maintains a queue of process control blocks. And as I said, let's say this is PCB1, then PCB2, then 3, then 4, something like this. Okay. So every process control block identifies a process uniquely. Okay, process 2, then process 3, then process 4. So if I give you a queue of process control block, indirectly I have given you a process of queues. So at the very first, let me make very clear. So whenever I am saying a process queue, it does not mean a queue of processes, it means a queue of process control blocks. Okay, then why I am saying a queue process queue? So when I am giving you a queue of process control block, that means I am giving you a queue of process as well. Okay, so now let's see multiple queues that your operating system maintains. At the very first, we'll be seeing this ready queue. Ready queue is a queue that maintains all the processes which are in ready state. Okay, again, when I am saying it maintains all the processes present in ready state, I mean it maintains all the process control blocks, okay, of those processes which are in the ready state. Fine, this is ready queue. Ready queue is done. I hope it is clear. So now let's see one more interesting queue, that is event queue. Okay, what is event queue and which processes do we maintain in this event queue? Okay, so we maintain those processes which are waiting for some event to happen. So what do I mean by saying waiting for an event to happen? One process may wait for a signal, okay, from operating system or from another process. Okay, as of now this thing will not make lot of sense to you. So when we will be going into synchronization chapter, then we will be seeing signal, wait, semaphore, those things. After understanding that thing, I mean that open synchronization related things like signal, wait, semaphore, mutex, we will be understanding what do I mean by saying event. Okay, so as of now just know one thing, one process may wait for some other event to happen other than IO. Okay, other than IO, one process may wait for some other event to happen. And what do I mean by that event? By that event, I'm trying to mean one process may wait for some signal. It might be from some other process or it might be from operating system. So such processes makes a queue and that queue is called event queue. I hope event queue is clear as of now. Okay. So we will be seeing in much more detail in the synchronization chapter. Then we will be understanding what do I mean by this event. So now we will be seeing this block queue. Okay. So what do you mean by block queue? Okay. I will be answering. Let's say a process is busy with the IO operation. Okay. So in which state right now this process belongs to? As we have already seen, when a process is busy in IO operation, the process is in block state. Okay. This block queue maintains all the processes that are busy in IO operation. Okay. So I will be coming to this timeout slightly later. Let's come to this point. Okay. So let's say some processes are busy in IO operation. As a result, those are put into block queue. So another information is each of the IO devices may have their own queue. I will be explaining the reason shortly. There might be a disk queue, there might be a printer queue, there might be a network queue. Okay. So why every IO device maintains their own queue? The reason is, let's say there is a disk. Okay, and process wants to access the disk, process 2 wants to access the disk, as well as process 3 wants to access the disk, and there might be some more processes wants to access the disk. Okay, so P1 says, hey disk, I have some business with you. P2 and P3 says the same thing. Okay, so disk says, okay, that is fine, but I have a queue, come and join the queue and wait for your turn. Okay, now let's see this queue, timeout or priority. Okay, so what is timeout queue and what is priority queue? Generally, processes are stored in the same queue for timeout and priority issue both. Okay, Fine. So timeout I have already said. There is something called time quantum. When this time quantum expires, that is timeout takes place. Okay. So operating system comes, takes the process and put into this particular queue. Same thing when some high priority task comes in, when some high priority process comes in, so low priority process is taken out from CPU and put into this same queue. Fine. So already we have seen this timeout thing in detail. So I am not explaining timeout again in detail. I am not wasting time in explaining timeout. Okay. Fine. So this thing is done. This thing is done. Fine. Then there is called something called suspend queue. So every operating system generally has two suspend queues. Okay. So what are those? One is suspended ready queue. One is suspended block queue. What is suspended ready queue? All the processes that are into suspended ready state, those are into this suspended ready queue, and all the processes that are into this suspended block state, those are into this suspended block queue. Okay. So these are the all the queues available. Okay. So there is something called job queue which I skipped. So job queue is all those programs. I would not say this is process. Job queue is all. I mean, job queue maintains all the programs which is trying to be a process. Okay. So job queue are all the programs which is trying to be a process. So LTS means, what does this LTS means? Long term scheduler. Okay. Long term scheduler comes in. Okay. And takes programs from this job queue and creates process out of those and puts all the processes into this ready queue. Okay. Fine. Then the short term scheduler comes, takes one process from ready queue, puts into CPU execution. Alright. And here if you see, there is something called, I already explained this, that is medium term scheduler. Okay. What it does, what it does is, from ready queue it takes the processes, puts into this suspended queue. Okay. Fine. And from suspended queue also these processes are again put into ready queue. Fine. Now, there are multiple queues, just like I explained. One is block queue. So from CPU, let's say some process is there which is waiting for some IO operation to be done. Okay. So those processes are taken from CPU and those processes are put into this block queue. When this IO is done, it is again put into this ready queue. Similarly, I already told there is something called event queue. So we will be seeing much more detail what is event is. So once we are into this synchronization chapter. So as of now, just know one thing. Sometimes some process may wait for some other event to happen, okay, which is not IO. Apart from IO, there are some events a process may wait for that. Okay. So when a process waits for such events to happen, at that moment those processes are put into this event queue. Fine. Once that event takes place, this process is again put into this ready queue. So again, there is another queue called timeout or priority queue that I have already explained. Once this timeout takes place or the time quantum expires or some low high priority task comes in, these processes, that process which is currently onto the CPU, this process is taken out from the CPU and put into this timeout or priority queue. Once this timeout again, once let's say some process is out from the CPU because of the timeout expiration. So after some time, again this process will get scheduled. But in order to make that happen, we'll have to push this process to the ready queue, right? So that is why this process is under again pushed into ready queue. Let's see this fork queue. Okay. So as of now, I have not covered fork. So as of now, I'll be giving very brief. So let's say there is a process, okay, and it has called this fork method, okay, fork function. So what happens is one more child process is created out of this parent process. So sometime it may happen that this parent process is waiting for this child to get terminated. Okay. So in those cases, if this parent process is waiting for this child process to get executed, then this parent process is put into this fork queue. Once this child process is done with the execution, what will happen is this parent process will be pushed into this ready queue. So far we have seen long-term scheduler has to wisely create processes so that it creates a good mix of CPU bound and IO bound process. Okay. This medium-term scheduler has to pick wisely which processes has to be pushed to suspended state. Otherwise, you will end up with lot of high number of discretes and discretes. Okay. So this long-term scheduler has to be smart. This medium-term scheduler has to be smart. And coming to the short-term scheduler, your short-term scheduler decides which process will be running next. Okay. So if this short-term scheduler is not working wisely, what will happen is you will end up with lot of context switches, and your performance will get a your performance will get heavily impacted. So combination of all these three are required to get a good performance out of your operating system. Okay. There is interesting thing. Let's assume there is a system with n number of CPUs and m number of processes. So let's say there are multiple states. One is ready, then running, then block. Okay. So in ready state, what is the minimum number of processes that can be present? Okay. So let's say all the processes are either on this running state or in block state. So what will happen? In ready state, you will be having zero number of processes. Similarly, let's say in running case, let's say all the processes are in the block state. Okay. Then what will happen? There will be zero number of processes in the running state. Similarly, for block state, okay. Similarly, for the block state, let's say all of the processes are either in ready state or in the running state. Then what will happen? There will be zero number of processes in the block state. Coming to max, okay, what will happen? It is possible that all of the processes are ready to run, okay, and all of the processes are in the ready state. So max will be m, which is the number of processes. Then in running state, what is the max number of processes that can be in running state? So already I have told you that if there is one CPU, only at any time only one process will be executing. So in multiple CPU, in multiple cores, in multiple core computers, multiple processes can be running simultaneously. Okay. So if there are n number of CPUs at any time, at max n number of processes can be in the running state. How is that? N number of CPUs, every process will be assigned to one, what do you call it, one CPU. Okay. So at the end, max n number of processes can be running at any singular point of time. So in block, what is the max number of processes that can be in block state? Okay. So let's say m processes are there, and somehow all these processes are waiting for IO. Okay. As a result, all of these processes will be into the block state. Hope this is clear.